Hello everyone, my name is Deanna Easley and it is a pleasure to give this talk for the SIAM Math of Planet Earth Conference. Today I will be discussing my research with Dr. Tyrus Berry on generalizing the unscented ensemble transform to higher moments. In this talk, I will go into the unscented transform and how we built off of it to create a higher order unscented transform. Now, some motivation. The most common application of the unscented transform is for forecasting dynamical systems. So let's consider the problem of forecasting the chaotic Lorentz 63 dynamical system as shown here. Take an initial distribution, marked in blue here, and the forecast distribution, marked in red. Let's focus in on these distributions. The figure on the left represents the initial distribution, and the one on the right represents the forecast distribution. We would wish to summarize the given distribution with a small set of points. In the example shown, the sample size of the distribution is 10,000. Rather than evaluating all of the 10,000 samples into the function, we wish to use a small ensemble to reduce the runtime. An important application of this is the Kalman filter. One of the fundamental questions we are trying to look into here is, given the distribution of a random variable x and a function f, what can we say about the distribution of f of x? Let's go into how the unscented transform works. The goal here is to estimate the expectation of f of x, which is an integral as shown here, where p of x is a probability density function. We can achieve this estimate by designing a quadrature rule to approximate the expectation. A quadrature rule is a weighted sum of function values at specific points called nodes. We say that a quadrature rule has degree of exactness m if m is the largest value such that all polynomials of degree m and below are integrated exactly. The unscented transform is a quadrature rule developed by Houllier and Ullmann designed to have the right nodes chosen so that the quadrature has degree of exactness 2, or another way to think of it is that it matches the first two moments of the distribution of x, the mean and covariance, exactly. The nodes that are used in the unscented transform are called the sigma points. Assume we're only given the mean and covariance, which both have dimension d. Then there are two d sigma points. The first d sigma points are defined as the mean plus the ith column of the matrix square root of d times the covariance. And the next d sigma points are defined as the mean minus the I minus dth column of the matrix square root of d times the covariance. Now, as I've been discussing this transform, I'm sure many of you have been thinking right now, what's with the name Unscented? What does it stand for? Is that some kind of technical term I haven't heard of? And, well, it actually doesn't mean anything. It was just that one of the creators didn't want the transform to be named after himself and came up with the name while looking at some deodorant, apparently. It's kind of goofy, but, well, maybe not so much if, maybe he thought that it was because the transform didn't stink. So, I guess We should give him credit for that one. Taking the corresponding weights to the sigma points to all be equal to 1 over 2d, the empirical mean is the sum of is 1 over 2d times the sum of the sigma points, and the empirical covariance is 1 over 2d times the sum of the product of the sigma points minus mu with its transpose. Because of the way the sigma points and the weights are designed, we have that the empirical mean and the empirical covariance match the mean and covariance exactly. Now, we're trying to consider the higher order moments, namely the skewness and kurtosis, which are tensors. So what are tensors? Tensors are basically multidimensional matrices. A tensor is said to have order k, in which case we call it a k-tensor if it belongs to r to the d to the k. In particular, a vector can be thought of as a 1 tensor and a matrix as a 2 tensor. Here we can see how the covariance, skewness, and kurtosis can be represented in tensor notation, where the skewness is a 3 tensor and the kurtosis is a 4 tensor. Now remember how eigendecomposition of a matrix works, in that it is in fact a rank 1 decomposition of said matrix. As shown here, we can write this rank 1 decomposition in tensor notation. Now recall that Houllier used the matrix square root of C for his sigma points. That actually comes from the eigendecomposition of C. These UI vectors are essentially the columns of the matrix square root of the covariance matrix. These UI vectors are what are used to generate the sigma points. So if we can get something like this for the covariance, it's only natural that this will be how we generate the higher order sigma points. And this motivates us to find rank 1 decompositions of the skewness and kurtosis in order to find new sigma points that can be used to compute the empirical skewness and the empirical kurtosis. To be able to discuss how we find the tensor decompositions we're looking for, we first need to discuss how tensor multiplication works. Let's consider the simplest case that we should all be familiar with, multiplying a 2 tensor with a 1 tensor. When dealing with tensors, we use this different kind of product notation that we call the n-mode product, where n is the summation index. We can see here that the 1-mode product, where we're summing over the first index of the matrix, is equivalent to the matrix transpose times a vector, and the 2-mode product, where we're summing over the second index of the matrix, is equivalent to the conventional matrix vector multiplication. Something to keep in mind here is that when we multiply a tensor by a vector, the order decreases by 1. So multiplying a 2 tensor by a 1 tensor will give us a 1 tensor, and multiplying a 3 tensor with a 1 tensor gives us a 2 tensor. So given a d by d by d tensor S, we can see that there are 3 n-mode products this time, since there are 3 indices, and these are how they are defined. To help visualize 3 tensor multiplication, let's consider a 3 by 3 by 3 tensor S and a 3 by 1 vector V. then S can be thought of as this cube of numbers, and the one mode product, S times 1V, is shown to be this matrix here. Now, moments of a distribution have this special property in which they are symmetric, in the sense that they are invariant under any permutation of their indices. And since all the moments are symmetric, that means that the n-mode product is independent of the mode. So we can go with whatever mode we want. So let's go with the one-mode product. Then we can define an eigenvector of a 3 tensor as S times 1V times 1V equals lambda V, with the component-wise definition being shown here too. Now we want to find the rank 1 decomposition in the following form. Now let's consider this theorem on tensor eigenvectors in general, which states that the eigenvector V of a k-tensor T, such that T times 1V times 1V, etc., times 1V, k minus 1 times, is equal to lambda V with absolute value, with maximum absolute value of lambda, gives the best rank 1 approximation of T, which is lambda V tensor K. And for numerical methods that can find the tensor eigenvectors, the methods HOPM and SHOPM are available. Other people have proposed that recursively subtracting the rank 1 approximation results in a tensor decomposition, and we have actually proved for the first time that this is indeed the case. After we found the rank 1 approximation lambda V tensor K, we subtract it from T, and then recursively find the rank 1 approximation of the result and subtract it from T once again, and repeat to get TL plus 1 equals lambda L minus lambda L VL tensor K, where lambda L is the largest eigenvalue and absolute value of TL, and VL is the associated eigenvector. So note that this is the best rank 1 approximation of TL. Assume also that there is a lower bound on lambda L. Then not only do the residuals decay to 0, but we actually recover a linear upper bound on the decay rate. Then the result is for T to be equal to the sum of all of these terms we're subtracting off. In this, right here, this will be our rank 1 decomposition. Now that we've found how we determine the rank 1 decompositions of the skewness and kurtosis, one issue that arises is that once we've found these, the moments of the eigenvectors that we find don't actually match the mean and covariance, which means we can't just tack on these decompositions to the unscented ensemble. So, what does this mean for us? Well, this means that we have to actually create our own set of sigma points. And that's what we did, along with corresponding weights, so that we have that the empirical mean and empirical covariance match the mean and covariance respectively, and the empirical skewness and empirical kurtosis approximate the skewness and kurtosis respectively. Now we introduce these new sigma points for the higher order unscented transform. Suppose we're given the first 4 moments and have the rank 1 decompositions of the skewness and the kurtosis. And let alpha, beta, gamma, and delta be constants, and these other quantities, mu tilde, c tilde, and mu hat and c hat to be defined as follows. Then the 4 moment sigma points and corresponding weights are defined as such. There are n plus 3 sigma points this time, where n is equal to 2 times d plus j plus l, where d is the dimension of the moments, j is the number of eigenvectors of S, and L is the number of eigenvectors of K. Ideally, these would be the rank, but we found that we needed a higher number. All of the moments affect each other, so we have to do this very careful balancing act. Here, we have that the first 3 sigma points correspond to the mean. The next 2d sigma points correspond to the covariance. The next 2j sigma points correspond to the skewness, and the remaining sigma points correspond to the kurtosis. With these 4 moment sigma points, we indeed have our empirical mean and empirical covariance match exactly the mean and covariance, and the empirical skewness and empirical kurtosis approximate the skewness and kurtosis respectively, up to an error term that can be made arbitrarily small. Now, for a visual representation of the 4 moment sigma points, given this distribution shown here, the black points are the sigma points corresponding to the mean. The green points are the sigma points corresponding to the covariance. The red points are the sigma points corresponding to the skewness, and the magenta points are the sigma points corresponding to the skewness. Kurtosis. Finally, we compare our transform to the unscented transform. We're using the probability distribution from the previous slide, and we're plugging it into various polynomials as shown here. And we're looking at how the error changes as we increase the strength of the nonlinearity. So the x-axis in these figures right here is the strength of the nonlinearity. HOUT is the higher order unscented transform, shown here in blue, and SUT is the unscented transform, shown here in red. We can see when estimating the mean how, with the quadratic functions, our transform is comparable to Houlier's, with minimal error close to machine epsilon and pretty much the same results for the quintic case. And with the cubic and quartic functions, our transform performs better. And when estimating the covariance, every case of function, our transform outperforms the unscented transform. Relating the results to degree of exactness, the unscented transform was designed to have degree of exactness 2, hence suited for quadratic functions, while our transform was designed to have degree of exactness 4, and hence better suited for higher class of functions. Now remember this from the beginning when we were talking about summarizing distributions for forecasting problems? Now these green points right here are actually the sigma points for the unscented transform versus the sigma points for our transform, which are in red. We can see that the sigma points for the standard unscented transform aren't really capturing all of the variation. You can see here that the red sigma points are capturing the full envelope of the distribution, whereas the green points are sort of in the middle, missing a lot. So applying this to the Lorentz dynamics, these are the prediction errors that we get. Once we compare our transform in blue to the standard unscented transform in red. And note here that the higher order unscented ensemble provides improved estimates of the mean and covariance. And now here are our references, and here is a link to where you can check out our upcoming paper. Thank you so much.